Hi, everyone. Welcome, welcome. Good afternoon. Hi, Professor Levy. It's good to see you again.
Hi there. Nice to see you, Sophie.
Welcome back.
Thanks.
Hi, everyone. Thanks for tuning in. I'm just letting everyone in from the waiting room. So I think everyone has officially connected to audio and can hopefully hear me. It's nice to see all of you this Friday. Welcome to this month's Jewish Faculty Lecture. I am Sophie Block, the director of Hillels of Memphis. I think I know everyone on this call, so it's nice to see so many friendly faces. This On One Foot Jewish Faculty Lecture Series is a virtual series that features a different Jewish faculty member from our local universities every other week. Well, actually, at this point, it's every third week or so, to spotlight the incredible Jewish intellectual and academic talent we have here in Memphis for the entire Jewish community to enjoy. So I'm so glad that you've tuned in today, because today's lecturer is Dr. John Hochstein, who is a professor of mechanical engineering at the University of Memphis and a longtime Memphian here. His scholarly interests are computational models of flows with free surfaces, innovations in engineering education, spacecraft cryogenic propellant management. I'm getting smarter just by reading this, okay? And flow and vascular aneurysm. So with that, I'm going to hand the mic over to our expert, Dr. Hochstein. Take it away.
Thank you very much. I forgot I did that stuff. It sounds interesting anyway. I will try and make this interesting. I'm just intensely interested professionally from the technical end, but I know not everybody is. So I'm going to try and make this as meaningful as I can in a more general way. So I'm going to start, I always start talking with somebody's quote, "People are smarter than me." So let me see if I can get this share working here. So there's a typical kind of thing I like to think about. I thought that was rather well put. What I want to talk about, a little introduction, one of the topics I'm technically interested in is sustainable energy systems. And I emphasize systems because it's not just where do you get it from, it's how do you use it. Since this is not a venue where, I can't do this in my classroom, but I can do it in this venue, is I've tried out a little bit of something that's meant something to me for a long time. And I take those words in a very broad sense. I think they were probably originally intended more in a spiritual, social justice sort of meaning. But to me, I take them to apply to our everyday quality of life. And I'm going to talk, but please, I'd much rather this be conversational. If you have a question, you want to voice an opinion, say something, please just talk right out. I'd rather have a conversation than a lecture. How important is energy? Well, I leave the engineers for a minute and I'll go to some historians, and this is the opinion of historians. Okay? It kind of tells you what role energy plays in our civilization and our social lives. Sustainable, well, I'm not a real great at definition, so I'll go do what any good student does. I go find some authoritative source. And I prefer sustainable to renewable. I know renewable is a popular term. I don't see a lot of distinction between the two, but I tend to prefer sustainable, something we keep doing, and is with a reasonable perspective, we don't run out of it. The sun will probably burn out in 4 billion years. That's not really our problem. So I already said this, but I harp on it. Today I'm going to talk mostly about acquiring energy, but I'll actually wrap up at the very end with just a quick hit on using it. And to me, one without the other is missing. It's like having, one slice of bread in a sandwich. It's an open face sandwich. It's not a whole sandwich. And I think everybody would agree we need to use it wisely, where we have differences of opinions. What does wisely mean? And so coming at it from a program management engineering point of view, say, okay, what are the issues? What are the concerns? What are the constraints? What is it that we're considering? And I think if we look at what we're considering, that's why everybody today will see things a little bit differently. And none of us will see things exactly the same way. So what we do is we look for common ground, shared ideas where we share about the same opinion on things. And for me, these are the kinds of topics that come to mind. I hesitate a little bit to put that survival of species at the end, but with everything that's happened in the last couple of years, and certainly climate change has gone from an archaic term to in the news at least once a week, maybe that's not quite as grandiose as it sounds, at least survival of a species in the way we know it, the way we're used to it. So I hope I made the case energy is important. It's certainly complicated. If we look back at the last century, life was a bit simpler. I mean, it really was the petroleum century. Again, I'll go to the historians. They'll tell you it was the petroleum century. We had oil before that, but around after the Civil War, especially in this country and other countries, we start to get more and more petroleum products. And you look at the 1900s, almost everything that happened is in one way or another connected to petroleum. In terms of energy systems, I like this picture. I like this picture because it pretty much tells the story. The way we get fossil fuels, the only thing I can think of that doesn't go back to the sun sooner or later is nuclear power. Whether it's wind or solar or hydrokinetic, sooner or later the energy is coming from the sun. In this case, it took millions of years to go from the sun to dinosaurs to decay, and we end up typically with these products. You know, we burn the gas in our car, coal for power plants and so forth. One of the things that's changed a little bit in this century is the idea of taking the energy from the sun and processing it much more quickly. And we've done some of that here in Memphis. I like to keep trying, today I'm going to keep trying to drag this back to Memphis. Okay, what's good for Memphis? What can we do in Memphis? And there's a reasonably vibrant group here in Memphis, in the West Tennessee, in this area. They're interested in biofuels. So instead of waiting millions of years, we use what we know about technology. And the nice thing about biodiesel, ethanol, syngas is we use them a lot like we used fossil fuels. We make heat, we do work, we make electricity, we run machines. So the use of them is pretty much what we've been doing in a big way for the last 100 years. Some other 21st century, now these were around before. I mean, people are a little surprised, but we knew how to make biodiesel fuel in the 1800s. There just wasn't a good reason to do it. As an engineer, I like to tell my students, just because we can do it doesn't mean we should do it. And typically should has to do with the economics. Doesn't make economic sense. Nobody's going to pay 5 times as much for biodiesel if they can buy fossil diesel, like I said, for 1/5 as much. So these aren't all strikingly new, but they're becoming more viable and we're getting better at doing them. I think some people look for a silver bullet. They look for, will this solve all my problems? Will that solve all my problems? And the reason that can't happen is we have different needs. You just look at the typical ways we use energy. You want to have a vehicle, like electric cars are coming on now. The problem with electric cars have never been the motor. It's always, how do you store enough energy on board to go where you want to go? Batteries are relatively inefficient. Gasoline is wonderful stuff. There's a reason we're addicted to it. But if you don't have a vehicle, if you just want to bring power to your house, electricity is wonderful because you can transmit it over relatively small wires, and except for the last week or two, it's pretty reliable. So these are all things, different things you have to ask. As an engineer, I may not like it, but political impact makes a difference. Some things are not politically viable. I'll come back briefly a little bit and talk about nuclear energy. The availability of nuclear energy has as much to do with politics as it does technology. I'm not saying that's bad, I'm just saying that's reality. So these are some options we're looking at that we have had and have now at our disposal. And one thing I like to emphasize when I talk about this is what's the true cost, not just the dollars, but what's the true cost? You have environmental impact. You have social impact. I'm going to come back to it later, but for instance, every time I go to the pumps and put a gallon of gasoline in my tanks, a lot of that money, very little of that money stays in Memphis, West Tennessee. Some of it goes to wherever the company is. And a fair chunk of it goes to whoever brought it out of the ground. So when I look at the true cost, I'm saying that's actually it may sound weird to have an engineer say it, that's a transfer of wealth. That's an economic, social question. I'm an engineer. You have to put up with just a couple of numbers, a couple of terms. I feel like I need to say them. You probably may have heard them in use before, but just to give you an idea, if you go out and buy an air conditioner, it's usually rated in BTUs, so many hundred, so many thousand BTUs. That's a British thermal unit, and it's not quite that anymore, but when it started out, it's easy to think that's how much energy it is required to take 1 pound of water and heat it just 1 degree Fahrenheit. It turns out energy gets stored in water very well. It's why we use it so much. That's energy. Power, these two get confused a lot. They get confused by engineers too. Energy and power are not the same thing. Power is how fast energy gets used. I'm assuming everybody here has experience with automobiles. You go out to buy an automobile, you want to know how much horsepower does my car have? That's how fast can it produce energy, typically because people want to accelerate. To give you an idea of the numbers, if I come back to electricity, probably all heard about kilowatts. If you get a bill, I'll get to this in a minute, you get a bill from MLG&W, it's kilowatt hours. So 1 kilowatt is 1,000 watts. 1 kilowatt is also about 1 BTU, close enough we can think about it that way. And since we talked about cars a minute, 1 horsepower is about 3/4 of a kilowatt. Just rough numbers I can carry in my head. So if I ask what I can do with it, well, first, what does it cost me? I looked up the MLG&W, yeah, they get that right. The residential rate as of January 4th was about 8 cents a kilowatt hour. That means you're going to burn 1 kilowatt, you're going to consume 1 kilowatt for 1 hour. They're going to charge you 8 cents for that. And to give you a rough idea of what you can do with that, 1 kilowatt hour will let you watch about 24 hours of television. Yeah, I like to convert things to something I can feel. And as my son who works for MLG&W likes to remind me, it's really more than 8 cents because there are fuel surcharges and everything else. But that's a place I can hang my hat. One reason we're hooked on gasoline like we have been is 1 gallon of gasoline has 36 kilowatt hours in it. 1 gallon of gasoline. Just imagine a 1 gallon milk jug. If it's gasoline, 36 kilowatt hours. That's why it's so great for vehicles. We can drag around this energy. I can fill up my car and drive 400 miles before I have to fill it up again. Okay, so for me, the reason we're in love with gasoline is because of the energy density and how we use it. Okay, so that's my commitment to doing a little bit with units. I feel like I've accomplished something there. Whenever I say I want to make something better, and I do want to make it better, I think probably we all want to make it better. Got to figure out where we are to figure out where we want to go. So this has got a lot of information, and I don't expect you to be able to read all of it. But this is a picture I pulled out of a Department of Energy, DOE, publication in 2000. It's 2006 publication. Don't worry about reading the details because I'll bring some bigger information on screen here. But very simply, this left side is all the energy coming into our national system, and the right side is how we're using it. So on the left side, I got to give you an idea of scale. I work in this stuff. I still find these numbers stunning. The numbers here, like down here, 22, 39, 104, are in quadrillion BTUs. So we just talked about what a BTU was. A quadrillion is a 1 with that many zeros. I get tired of counting. Okay, so all these numbers are quadrillion BTUs. You can imagine engineers get tired of saying quadrillion BTUs, so we call them quads. If you hear somebody talk about a quad, they're talking about a quadrillion BTUs. This total supply right here is pretty much how much is going through your system is 105 quads. So I put 105 in front here. This is how much energy went through our system in this country in 2006, just our country. 105 quads. The nice thing about 105 is it's pretty close to 100. So if I think about these numbers as percentages, I'm not too far off. About 24%, about a quarter of the energy came from coal, burning coal. About a fifth, natural gas. We do some things with crude oil without turning it into gasoline or diesel or something else. Nuclear, 8%, renewable, 7%. And we actually, in 2006, we imported a little less than a third of the petroleum we used. One thing I'll point out here and in the next slide, which is a newer version of this, that's where I'm headed. I'm showing you 2006. I'll show you something that's only about 3 years old now. This renewable 7% most of that was built during the Depression or earlier. That's the big hydroelectric dams, Hoover Dam, Bonneville Dam, the dams we have in Tennessee. So while it's nice that we've got these, this stuff's getting old. Nobody wants to talk about old dams. They're expensive to fix, expensive to replace, but we are going to have to face that sooner or later. Anyway, here's where energy's coming, where it's going, how we're spending it. We spend about a fifth of it to heat or cool our homes. The difference between commercial and industrial, the easy way to think about it, industrial is factories, commercial is office buildings, school buildings, anything that's not a home and not a factory. And so you can see we spend a little more than a quarter of it on transportation. That's quite a bit, but I'll put in my own plug. Every time I hear Congress argue about CAFE standards, fuel economy standards for automobiles and trucks, I go, well, that's nice, but that's only a small piece of the problem. That's less than a quarter of the percent here, because this transportation includes things like boats and trains. So for me, this is a picture, what's coming in, what's going out. And if I had a punchline to this whole picture, I'd say it's a steamship. You think about a steamship, if you want to turn or you want to stop, it doesn't stop right now. You say, I'm going to start to slow down. I'm going to start to change direction. It doesn't make a right turn like we do at the corner. This system is so big that anything we do today, even if it's massive, takes quite a while to change the direction we're headed. I feel like I've been doing a lot of talking. Any questions, any comments, opinions? Okay, I'll keep talking, but like I said, don't hesitate to jump in. Now here's a picture. I regrettably didn't put down the date, but I think this was from 2019. The same publication, it's EIA, DOE, same people, Department of Energy, and it's the same kind of picture. I intentionally like the fact it's a different color, and it's got the same kind of information. So now the supply went from 105 up to 122. So in a little more than 10 years, we went up about 10%. Here's where it's coming from in 2019. And in a minute, I'll put up some numbers to give you a comparison. But you can see here's coming. Nuclear went up just a little bit. Renewable, nice. It went from 7 to 11%. Most of that change is new stuff. So that's a good thing. That's encouraging. That's the wind, solar, all the renewable, sustainable energy things you hear about in the news. And well, we're using a little bit less. This was a little bigger number for our homes last time. Transportation went down just a touch. Industrial went up a little, but there's not a giant shift. If I try and bring back some of the old numbers, that was 105. Coal was 24, so that's a nice improvement. Coal is great stuff in terms of technology being easy to use, but as you all I'm sure know, it's not so wonderful in terms of environmental impact. For better or worse, we live in TVA country, and TVA is more reliant on coal than most energy systems around the country, and that's a historical thing. It's not surprising. It's an older system, but that's down a little bit. That's a good thing. Renewable went from 7 to 11. I think that's a good thing. Oh, let me go back. So things have moved around a little bit, but not giant shifts. Yeah, this breaks out a little more detail right here. Nuclear power is actually up to about 8.5. It's fascinating to me to look at nuclear power. Like I said, it's as much about politics as it is in economics and technology. But we can talk more about that if you want. There's some interesting innovations now in nuclear energy that might make that come back, at least be a bigger. None of these is a silver bullet, but the more we grow something other than fossil fuels, the less environmental impact we're going to have in general. It's generality. Sweeping statements are always dangerous, but in general. So what are our options? I'm going to talk a little about all our options, but I'm a homer. I want to see what can I do in West Tennessee? What's good for Memphis? Solar, wind, geothermal. You've heard about all of that. If you're not familiar with geothermal, very quickly, you drill a hole till you get to a hot spot, and then you use the heat. Pretty much in engineering, as long as you've got a temperature difference, you've got something that's hot and something that's cold, you can make power. Conventional hydro is what I mentioned before, which you think about dams, hydroelectric plants. Hydrokinetic, believe it or not, has been around for centuries, but we don't think about it that much. I'm sure you've all seen the old grist mills, right? There's a pool or a river, and you have the wheel. The water goes in the wheel, makes the wheel turn, you grind up corn. That's how long it's been around. Hydrokinetic means that there's kinetic energy in the moving, typically water, or if it wasn't hydro, it'd be wind. And think about it, with a windmill, you don't bring the wind to a stop. You harvest some of the energy and it keeps on going. And that's the same way it was with the old grist mills, and that's what hydrokinetic energy is. How can we capture the energy that's in this moving water, whether it's a river? Biggest river I know is the Gulf Stream out in the ocean. So as long as I say naturally occurring flow of water, and you can capture it, do something with it, that's hydrokinetic. Usual suspects, nuclear, boy, do we ever really rely on chemical energy. We're relying on it right now to make electricity. And at least I don't know about you, but right now I'm on my laptop that's got a battery in it. Thermal differences can be from also in the ocean. I'll just mention that quickly. It's not going to work much for Memphis, but you go out to a large ocean, there's a big temperature difference top to bottom. On the top, it's warm, the sun beats on it. Go down 100 feet, 200 feet, 300 feet, it gets cold relatively. As long as I have a temperature difference, I can make power. I can make electricity. Stored mechanical energy, I have to admit I have a soft spot for that because I'm a mechanical engineer. But there are parts of the world where we make electricity, they make electricity either by winding up a spring, or if you think about it, you've seen in the old days, the trebuchets, you throw the rock at the castle you're trying to take. You have stored energy. There are places in the world where you hang a weight, and as gravity pulls it down, the chain or string spins a generator, makes electricity. Not particularly attractive to us in Memphis, but that's real attractive if you have no power at all. Fossil fuels, and I'll come back one more time, each one of these has a price, and it's not just a monetary price. It's an environmental impact price, it's an economic impact price, and I believe in often a social impact price. So I'm not sure, this is probably not what the business school means by full cost accounting, but for me, full cost accounting means looking at the whole picture. So here's a picture. I went back, the U.S. Department of Energy is a great resource for information. Picture of the U.S. I don't expect you to read any of this because I can't, but pretty much purple is where there's a lot of wind. Red, there's a little less wind. We've got no wind. Okay. I always have some students that want to do a senior design project to look at building a windmill in Memphis. And sometimes we let them do it because it's a good exercise. But a rule of thumb, unless your average wind speed is above 8 miles an hour, there's no point in putting up a windmill. And it just isn't. Wind is not a good answer for us. It's interesting to me. It's a great answer. Lake Michigan is a great place to put up a windmill. It's close to where we consume energy, Chicago, Detroit, cities like that, Milwaukee. It's shallow. It's easy to put up windmills. And all I do is look at this picture and go, wow, they got a lot of wind. So wind's not going to help us here in Memphis. Let's try something else. Solar. We are putting up solar panels in Memphis. I'm not saying we shouldn't. But if I look at this map and say, okay, I I don't like a level playing field. I want a playing field where I have an advantage. Memphis doesn't have much advantage over Montana and North Dakota. That doesn't mean we shouldn't have solar panels in Memphis and North Dakota, but it's not a particular advantage to me. So I'll look around a little more. Oh wait, I almost forgot. There's a picture. This is actually a picture. I think it's the solar farm out at Shelby Farms. And the solar park at Shelby Farms is more I'll say a demonstration than what I would consider a commercial operation. It only makes about 1 megawatt, which may seem like a lot of power, but it's not on a commercial scale. In order to make that, you got to have 4,000 panels. Remember, I said full cost accounting now. I've got to take 5 acres and either make it dual use or exclusive use for this. Now, people are starting to get smarter about dual use, finding other ways to have solar panels and something else going on. But if I don't, I've taken potentially 5 acres out of production to make power.
John, I have a question.
Sure.
Could you put solar panels, let's say, on your roof and have enough power to power your house?
Interesting question. Sometimes. In Memphis, sometimes. MLG&W will let you do that. The laws are interesting because we live in TVA country. You can make as much power as you wish for personal consumption, but you can't sell it. Okay. If you make power, you need to sell power to TVA and then they'll resell it for you. As far as your own personal use, I don't have that, but my understanding is you can put it on your roof and you get wired into your box and you can use it instead of using MLG&W. And if you make excess, you can actually sell it back to MLG&W, who in turn, I'm sure must be selling it to TVA. I'm not sure. I don't know the legalities of all that. But I see it as, in Memphis, I see it as something that might be good for the environment. Financially, I'm not sure how many years you have to go out to pay for those panels in the first place. But I never say never, because my experience is technology always gets better. One of the problems with these panels is they're really not very efficient at all. For how much sunlight lands, you don't get much electricity out, but that gets better all the time. And then another problem, since I'm on this full cost accounting thing, making solar panels is not without its own problems. It requires materials and processes that aren't necessarily environmentally friendly. And as long as I'm on my rant, I'm not sure we figured out what to do with these when they don't work anymore. So the catchphrase is cradle to grave, but I like to think about this, the entire, not only the full cost, but the entire spectrum. How do I make it? What does it do for me in operation? And sooner or later it wears out. What am I going to do with it when it wears out? That's a good question. Thanks, Marion. I think I've been aware. I think most. Sorry.
Doctor, what do you think about fracking? What as an option?
I think fracking is scaring me. I've heard too many stories about damaging the groundwater, and if there's one resource we have in Memphis that's precious, it's that aquifer, and I think rightly so. Anything that jeopardizes that aquifer, it's just not going to happen. It's not going to happen politically. I hope it won't happen politically. So, well, you say I'm fracking in the middle of Wyoming. What am I going to hurt? Well, I'm not sure what we're going to hurt. One thing I'm not a fracking expert, but I've read a bit about it, and there's more than one way to do the fracking. And unfortunately, the more efficient, cheaper way to do it is the one that's the most harmful to the environment. So does it have a role? Perhaps. One thing it has done is distorted the entire energy economy. Since I took a right turn here, I will for a minute. We actually built a biodiesel micro refinery in our building about 15 years ago, when biodiesel was economically viable. And I still think it's great stuff. And I think it's better than ethanol. That's my own opinion. And what happened is when fracking came along, the market dropped on natural gas and other petroleum, and it just, right now, biodiesel has a tough time being economically viable. So I'm not a fan. I hate to say don't ever do anything, but I would certainly not like to see any fracking around here. That the aquifer is way too important to me. Anything else somebody wants to discuss? I'd much rather talk than lecture.
What about the hydroelectric possibilities of the mighty Mississippi? It seems to me we have a huge source of water. The problem is shipping might interfere with it, but I've got to believe something might work.
That's a great point. Everybody on this call looks to be old enough to understand, remember the reference. I feel a little bit like you're Ed McMahon and I'm Johnny Carson. Okay, because you just set up the last several slides I've got. So thank you. I think it's a fabulous resource, and I'll get there in just a couple of minutes. Thank you for the question. Okay, so Silicon Ranch, if you haven't heard about it, is in Millington, and you look at the numbers, it's 53 megawatts. It is a commercial operation, and if you want to go look at that online, you can. I see I'm starting to get wordy. There's a reason they call us professors. We like to talk. Geothermal is just not a good choice for Memphis. This gets back to that biofuels thing. Again, U.S. purple, red is a lot of vegetation, a lot of growth. Some of it's food crops, some of it's natural trees, weeds, whatever. But you look at the U.S. and there's pretty much 3 regions. You make biofuel over here in California, you're knocking off a lot of fruit and vegetables. We made a lot of ethanol up here. That's Iowa, right where my arrow's pointing. And what we discovered was you make enough ethanol, you start messing with the food chain. Because now you're using your corn to make fuel instead of making corn syrup and cornmeal and all the other things corn goes into. We are right here. I've heard someone else say, here's Memphis, right there where my arrow's pointed. I've heard somebody say if there was a state of the Mississippi, I'll say vegetation area, heavy vegetation area, Memphis could be the capital. What's different about where we live is there's far more variety in terms of crops we eat, natural vegetation, even just variety in the vegetation. So we have the potential to do biofuel here. Here's a summary of what I was talking about. Yeah, we don't have the right geography for dams. Nuclear is a conversation maybe for another day. Biomass is what I was talking about. We have but even with that, what's nice about biomass? It's sustainable. You can grow a crop. In some places, you can grow 3 or 4 crops a year. Okay. What's great in terms of climate change is it recycles the CO2. It actually pulls CO2 out of the air and makes oxygen. I'm always in favor of oxygen. Fuels are similar, easy to use. And what attracted me so much to biodiesel is the dollars stay in the local economy. If a farmer between here and Dyersburg grows a crop, we use it to make biodiesel, everywhere along that production line, the wealth stays in West Tennessee. So that's a plus. So minuses, I already told you, we found out the hard way. Pay attention to your food chain. The priorities are oxygen and then food. And one of the problems of biomass is the feedstock has low energy. In other words, you have to bring a lot of it to some point to process it to make the fuel. So it's expensive to transport. Thank you for the question. You were asking about hydrokinetic energy, and I told you I'm a homer. So that's what got me interested in hydrokinetic energy. That is a fabulous river we have over there. And we've actually measured it. We went out, this is very high tech. A couple of us went out and took a milk jug. No, it wasn't a milk jug, it was a 5-gallon, like a jug, 5-gallon water bottle. And we threw it off the bridge. And some other people were standing down at the other bridge, and we timed how long it took to go between the bridges and figured out that right in front of Memphis, that river's going about 5 miles an hour. That's high tech, that's what we did. The question is, can we put it to work without bringing it to a stop? And as that question, I'm sorry, I lost Yeah, okay, I can see that question pointed out, we can't mess with the transportation. If there's one thing I've learned in the last 10 years is if you think the railroads have power, you haven't seen the control that the barge people have over the river. Okay, and I understand that. It's a real economic artery. So what are we doing here in Memphis? That's a picture. If you can see in the distance, there's the M Bridge. Up closer, there's the railroad bridge, the Harahan Bridge. So we're standing on a barge that's moored up against the Memphis side. And this is an invention. It was invented by someone here in Memphis. I was a helper. I wasn't the inventor. I've been involved with the project ever since. In fact, this is Jeff Green standing back there. He's the inventor. The rest of us are involved with this project. We were trying to get TVA interested. They wanted to see a proof of concept. Okay, we have no funds. Okay, this what you're looking at was built in Jeff's backyard. He's pretty good with his hands. You want to talk about crude? These are just tubes that are joined. You're looking at flat pieces of plywood painted white for the blades. But for a proof of concept, this works. So we took this little by little. This picture is probably about 8, 9 years old already. I lose track of time. You see, we got a crane. People from TVA came to look at this, went ahead and hung it off in the river. And as the river goes through, it puts torque on the blades spin. And what's going on inside this invention is we're building a dam. It may not look that way, but the big wheel is really just a pump that keeps lifting water, not the river water, but inside here, this is maybe half filled with water, keeps lifting water. And then it's hard to see in the middle, but when the water falls, it falls through the middle. In the middle, we've got a turbine. Just like a conventional dam has a turbine, the water falls through it, makes the spin. We're making it spin. So we took this, we stuck it in the river. Oh, let me go back. And we made some power. Ran it for a couple hours. It really worked badly. I mean, it's not a high-tech thing. And first time we stuck it in the water, but we said it's not smoke and mirrors. This concept works. We make power. And one reason I like to show this to my students is because sometimes they think, well, you know, Silicon Valley is over there and these inventions are happening somewhere else. And they don't realize there's some pretty creative stuff going on here in Memphis. And the other thing they always get a kick out of, I point out that this is not exactly my best side. Okay, so that's one thing that's going on in Memphis. And that question was right on the money. The amount of energy that's going past us every day is enormous. And the great thing about it, now I'm going to my sales pitch. The great thing about it, it's going, when that river is going towards New Orleans 24 hours a day, 7 days a week. If that river is not going towards New Orleans, we have much bigger problems than making electricity. Here's another concept. There was someone else, I don't know if anybody here might have known him. John Willingham was the instigator for this project, but it's kind of the opposite idea. I'll go back. This device is really intended to be completely submerged. You don't really want to operate it at the surface. On the other, which has advantages and disadvantages. The advantage to this thing is it operates at the surface. It floats on the surface, and in its simplest form, just go back to the old steamboats. And instead of making the wheel push the boat, you hold the boat still and you let the river spin the wheel. We're almost back to the old grist mills, a little higher tech. Here's an artist concept I picked up off the web somewhere. It wasn't even ours. I think that might have been from the Netherlands or somewhere like that. So that's a project that's going on. There's still a group trying to develop this. And personally, I had a master's thesis student take a look at this problem. This is really a tough problem. You got the river going through here. You've all seen nozzles. You have a nozzle on the end of a garden hose. You use a nozzle to increase the speed. And I promised I wouldn't get too math on you, but if you double the speed of the water, you quadruple the power that you can get out. So if you can accelerate, that's great. So what you're looking at here in the artist concept is a nozzle. You're trying to gather in the water and accelerate it. Actually, look at this picture. I can't tell what's the front and what's the back, but it doesn't matter. What makes this more complicated than a garden hose? With a garden hose, all the water coming through the hose has to go out through the nozzle. With this, the more I squeeze down on my nozzle, the more the water wants to go, don't even go through the machine, go around the outside. So what Mr. Yan did, and we did this with some computational modeling at school. So this goes back to what Sophie said. One of my things is writing software to model fluid flows. This is a converging, diverging, a nozzle, and then a back opening on the backside. And we looked at different contractions to try and optimize how much power we can get going through the middle. And I was very happy. Not only did Mr. Yan do good work, but we were able to show there is an optimum. If it's too wide, you don't accelerate enough. And if you squeeze it down too much water goes around the outside. So there is a maximum, there's an optimum. Engineers love to find optimums. So that's just a quick hit on some stuff that's going on in Memphis, and thank you for the setup for that. But being a homer, I'm still actively involved with these. These are ongoing things here in Memphis. They're things that we have an advantage. We had a fabulous river right there. Most people don't. I told you I'd circle back at the end for a little social justice. This is a picture I picked up to be fair. I usually put dates on. I think this picture is about 10 years old, but it's average cost of gas per square foot by zip code in Shelby County. And they mean per square foot of building. They don't mean per cubic foot of gas. And the point I try and make with my students, the darker the color, the more you have to pay to keep your place either hot or cold, winter or summer. And so what you see here, and everybody on this call, I'm sure, is somewhat familiar with the neighborhoods. The people who can best afford the gas are the ones that need it the least. The people who can least afford the energy require the most of it. So, we could certainly talk for a while about this too, but it's my way of circling back to saying, although I am fascinated professionally by all the energy system stuff, I'm also somewhat driven when I step back and look at it in terms of societal impact, the impact on everybody's lives. So that kind of, Sophie told me an hour. I told her I'd take a half hour. I guess we were both about half right. I seem to have split the difference. So a few closing thoughts. A lot of people out there smarter than me. He certainly was. Kind of like that definition. Students ask me, what's the environment? Everything that's not me. You may be familiar with Buckminster Fuller, geodesic domes, buckyballs. This spaceship Earth theme got a lot of play. There's a next one, believe it or not, coming from an engineer as a poet. Oh, no, it's not. Yeah, that is. Marshall McLuhan. No passengers on spaceship Earth. We were all crew. And I didn't realize this till I was getting ready for this presentation. That sounds almost like where I started. I am not responsible for fixing all the problems, but I'm part of the crew. I'm supposed to help make it work. Barry Commoner, famous early advocate of consumer rights, ecology. I did go back to the Talmud, and I tell my students that. I say, I will do my best to help you learn, but I can't make you learn. So I really appreciate your time. I hope it's been of some value to you. And I was really open to spend as much time answering questions, talking about anything you want to talk about. Oh, thank you. Thank you. Thank you. Oh, I rarely get that response when I talk at school.
Thank you, Dr. Hochstein.
You.
That was fantastic. Does anyone have any more questions or feedback?
Hey, Sophie, it's Melinda.
Hey.
I have one question. Going back to the slide about the gas prices and the usage and the need, I guess I'm not sure I understand. Why is it that the people in that area that, have the darker areas, when you said they need it more, but they can't afford it? Like, how do you, when you say need, what are you defining as like?
I'm sorry, I was fumbling with the slides. I was going to try and put it back up. Take me half a second here. Well, to be fair, a couple seconds, but is that back up?
Yep.
Yep.
Okay. I think I never had it explained to me, but I'm pretty sure what we're looking at in a lot of ways is whether or not your house is well insulated, whether you can afford the double pane windows and the good insulation, at least for residences. And for non-residences, I suspect you're just looking at some really old buildings that people haven't renovated. So for me, this is more of this is the other side of the equation. It isn't the production, it's the consumption. And it just, maybe ironic's not the right word, but it kind of almost hurts that the people that need it the most have it the least.
And John, I can add from a public health perspective, that map mirrors the rates of diabetes, hypertension, cardiovascular disease.
Oh, wow.
Yeah.
Okay.
Thank you. That helps. I appreciate it.
Yeah, sure.
Thank you, Doctor, for your presentation. It's amazing to hear all the information you have. Would love just to, if you wouldn't mind, giving us your thoughts about what's happened in Memphis in the past week with the ice storm and the implications for the possibility of buried utilities in the future, whether or not that's practical, and just would love to hear what your thoughts are.
Well, I'm smiling so much because it's a softball. I appreciate it. Because I've had a little rant going on for the last week myself. Some of my friends get tired of hearing me. But full disclosure, I didn't grow up in Memphis. I grew up in the Northeast. I've been living in Memphis now 31 years. So I'm not a native, but I'm a Memphian. And I've lived in much harsher climates. I'll just tell you, Northeast Ohio, okay? Winter's brutal up there. Almost never lose power. The difference is the power lines are underground instead of overhead. And as I told you, my younger son works for MLG&W, so I've got an interest in this. And there's two things going on, at least that from my perspective. One is MLG&W is controlled by the city council. We're unusual in that we have a publicly owned utility. So some decisions are driven by that. And the argument is that taking all those power lines and burying them is too expensive. And it would cause rates to go up. And I understand nobody wants to pay high electrical rates. But I will point out, as far as I know, on a national scale, we have not the lowest, but relatively low rates. And to come almost back to that picture we were talking about, the people who can afford this the least get hurt the worst. Where does power come back up the fastest? And I was shocked. I didn't know this until I was watching television a few days ago. What they call the power head, the piece where the electrical power comes to your house, kind of like where the meter is and stuff, belongs to you. It doesn't belong to MLG&W, which means that if it got damaged in the storm, you got to pay to fix it. You call up MLG&W, they turn off the power, you hire an electrician, and at least now I'm telling you what I saw on TV, which is always a little suspect. I like to have a little stronger source than that. But they were saying this could be anywhere from $500 to $2,500. So these are the people the city council's trying to protect with low rates, getting stuck with $2,500. Now, I feel fortunate, you know, if the power went out to my house and I paid $2,500 to fix it, I'd be on the phone in about 2 seconds. But I think in a lot of those areas, $2,500 is a major challenge for them. So my completely take the politics out of it completely from an engineering point of view. What makes the most sense is say, okay, it's going to cost a fortune. We can't do it this year. Let's come up with a plan. Whether it's 5 years or 10 years or 15 years, I don't care how many years it is. Just come up with a plan to put all that power underground. Does it solve all the problems? No. But we'll just tell you, you triggered me by asking about the last week. Most of last week wouldn't have happened if the power was underground. I'm sorry if I got carried away there.
Thank you. Good question, Hal. Anyone else have a final question for Dr. Hochstein? Well, if you do, I'm sure you know where to find him. If you need me to put you in touch, I'm happy to do that. So thank you again, Dr. Hochstein, for your incredible lecture and discussion. It's such a luxury and a blessing to get to learn from you today. So thank you for being here, and thank you to everyone who tuned in. I will do a final plug for next month's faculty lecture, which will be on Friday, March 11th, right back here on Zoom at noon, with Professor Sarah Ift Decker, who is a professor of history at Rhodes College. And she's relatively new to Memphis. She came to Memphis and started teaching during COVID in the 2020 school year. So you may not have even met her or heard of her yet. So I'm really excited to bring her to the series. So again, that's on March 11th. And in the meantime, everyone, please stay healthy and safe. And we'll see you next time.
Thank you. Great job, John.
Thanks. Oh, thank you. Appreciate it. Had a good time.
Bye. Thanks. Shabbat Shalom.